So, was that? Yeah, I don't have to. Okay, so welcome back. So, yeah, this afternoon's schedule, we have various presentations by the participants. We'll go forward, take a short break for, and I said aim for 5 minutes, but we have a more relaxed schedule, so you can stretch that a bit. But anyone who abuses it won't get dessert the barbecue. But anyway, so we'll start with our first speaker. Wei-Yang is going to tell us about hadronic structures. So, Wei-Yang, and I'll record these for you and put them up somewhere so you can do them later. All right. So, thank you.
Thanks for this introduction. And I'm Wei-Yang Liu, and I'm a local student here in the fourth year PhD. And I work with Ismail Sahed, also the local professor here. And our research topic is about mostly the vacuum. And then we want to know right now that how the vacuum affect or how the vacuum determine the hadronic structures. Okay, so first.
The top one should be the pointer.
Okay.
It takes a minute to.
I go back.
Oh, the bottom one should go back.
Okay. Okay. So the first question is how to describe non-perturbative physics from the QCD analytically. We already know that we have the numerical tool, which is lattice QCD, very powerful. But lattice QCD has some intrinsic problems still like in progress to solve. Like we know it's hard to calculate the topological charge distributions. And we know that if the theory only have left-handed fermion or right-handed fermion, then it's also hard to use lattice QCD so far. And also, especially for the hadron or like a QCD community, the gluon operators, if you have the hadron source, like if you have a gluon probe, then it's also kind of noisy. So it's hard to get the information from those noise background. And also sometimes it could be resources demanding. So here, sometimes we will need some analytical tools, which is directly describe the non-perturbative QCD so that it can bridge the non-perturbative and perturbative QCD and provide some guidance or like some preliminary point of view for the lattice QCD people to see then what exactly they should go for to calculate. Okay, so this is a QCD vacuum. This is what they call the buried treasure in the sand of the QCD vacuum. So I think we already are very familiar with these pictures. So the vacuum structure in the QCD actually is very non-trivial. There are a lot of dynamical, a lot of like bubbly structures keep popping up. And what exactly these structures? So let's see, let's break it down. Okay, here. So we know the QCD vacuum is degenerate. They have infinite QCD vacuum states. So we label those states by the numbers we call Chern-Simons numbers. So here's a 0. Here's a 0, 1, 2. And then the physical meaning of this number is just how you wrap around. It's like a Whiting number, how you wrap around the vacuum configurations. And we know we have infinite of this. And then for the perturbative QCD, the calculation is just among this energy, lowest energy state, and expand it around. So you can see there's a full landscape that cannot be captured by the perturbative QCD, which is why we need a non-perturbative QCD to do some calculation. And among those configurations, there's one thing that we are focused today, which is the incentone. It's a tunneling event between different vacuums. So initially the QCD state is here, and then it tunnel to another state, different vacuum state. And the configuration induced this transition is we call it incentone. Okay, so from the a little bit field theory point of view, the perturbative QCD is just trivial vacuums. So if you want to go to low energy, you integrate over this Feynman diagrams, which is the UV fluctuations. then you will see it's nothing. But then actually, the vacuum is non-trivial. So we need to include those background non-trivial vacuums. So when you go integrate over those UV degrees of freedom, and then you will see there's a non-trivial effective field theory. Okay. So after we integrate over it, and then we can see here's the first part, the visualization of the QCD vacuum. And then here, this picture is a higher resolution of the that one. And you can see this bubble. Now we know it's incetones. And then except for this incetones, we also have this long string-like structures, and we call them center vortices. And we already know that incetone doesn't induce confinement, but it induces chirosymmetry breaking and other anomalies. So where's confinement? Mostly people will claim that it's coming from the center vortices, but it's still debating, but most people believe. Okay, so here, remember we integrate over the UV degrees of freedom. Now let's see what we have in the low energy. So the gluon degrees of freedom are integrated over. So we have this remaining of the incetone inside the vacuum. And then when you put the quark in the background of this bubbly picture, and then you will see the quark will scatter by this incetone picture. It's just like you have a material, and then now you put the electron in this material, then this quark will start to conducting. What's a charge conducting? They are conducting, it's a chiral charge or axial charge. So then you will see it's a beautiful picture of the phase transition. It's a spontaneous symmetry break. Will give us a spontaneous symmetry breaking. Okay, so now we know how the quark passing through the vacuum. Now we put the hadronic source, just like on the lattice QCD. So the hadronic source here, they will emit this quark states from the source, and then they will interact with the vacuums. And different hadronic state, they will interact with different vacuum structures. So this allows us to calculate the hadronic state, and then of course the hadronic structure. So now we can see the result. Here, first of all, the important thing, we have to be able to reproduce the mass spectrum. So here we can see we can calculate the pion close to the PDG. And here's the parameter we use. Rho is the size of the incetone. You see the picture of those bubbly structures, the blob, it's a size. The size is about 0.3 Fermi. And the density, it's like how many blobs in this one big box? It's like 1 Fermi to the -4. So we can see this is around like 200 GeV to the 4, and this is around 600 GeV, MeV. Okay, so this is the mass spectrum. And then we can also calculate, because we know the parton structure function like parton distribution amplitude, parton PDF, those are non-perturbative objects. So we are able to calculate them. And then you can see we compare with the lattice and the experimental data, even though this is a little bit old experimental data, but we can still see that the green line here, it's very consistent with the lattice and also the experimental data. And we can also calculate PDF. And here the purple line is the refeeding of the old experimental data. So the purple line is a new curve feeding from the experimental data. And then we can see the incetone model is the orange line over here. So it goes well with the purple line. Okay. And then now the next question is, now we have a low energy effective theory, but we already have chiral perturbation theory and some other quark models. So what makes it different? It's because in low energy, we know gluon is there, but those model doesn't explicitly show you the gluon degrees of freedom. So if you want to calculate the gravitational form factor or like trace anomaly, something that include the gluon or like gluon PDF, they have the gluon degrees of freedom. That would be hard. because those model doesn't have gluon. But here we show you that because our model have this gluon decrease of freedom, so we are able to calculate the form factor, for example. The gravitational form factor for pion, we have A and D. I think people already know from the Yoshitaka's talk. And then we can see that here, the blue one is from the lattice group from the Fiala, from the MIT. And the red one is our full calculation from the incerton. So basically, we know that when you go to high energy, the perturbative gluon becomes more and more important. So we have to consider the perturbative contribution over here. That's why we have this soft curve and this hard curve. And then eventually we interpolate these two curves, become a red curve by the optimal fittings. Okay. And the next one is the big question about what's the percentage of the quark contribute to the mass of the nucleon, and what's the percentage for the gluon? So we can see the lattice calculation, they have this nice plot, 36% for the quark and 32% from the gluon. This is from the energy momentum tensor, but there's quark mass, which is the mass from the Higgs mechanism, and also from the trace anomaly. And then you can see if you compare the the incerton calculation, then it's very close to this plot. So you can claim that mostly the non-perturbative structures, especially for the pion or like those light hadrons, it should be dominated by the incertons. Okay, the last one is we also calculate the diffractive heavy meson productions. So usually when you use the factorization, then the proton has to move in very fast. But in the near threshold regions, usually the proton will move very slow, so you cannot factorize it. But it's not the case when the meson is heavy. When you produce the heavy mesons, then the proton is forced to move in very fast. So you can still use this factorization regime. So our calculation is in the regime near the threshold, which means the center of mass energy is roughly equal to the mass of the proton plus the mass of the heavy mesons. And we can calculate the differential cross-section here. And you can see that this is the lattice calculation and also the experiments from the GluX and JPSI 007. And the red line is our calculation from incerton models. And then you can see it's consistent in the arrow bars. And except for this 2 gluon probe, we also have the 3 gluon probes. And sometimes people will say this is related to the Pomeron, this is related to the Odderons. And we can see that we don't have the experiments result yet from this part, but we compare with other phenomenological models from the Bartos and Eagles and Jasinski. But you can see the inconsistency over here. The reason is our model mostly work in the near threshold, but you can see the center of mass is here, it's 300 GeV. So we just like extrapolate our result to the very high center of mass energy. But then you can still see the difference between the gap is not dramatic. Okay, so the summary of this is just, so we know the vacuum structures, the non-perturbative physics, it has to come from the vacuum. And then we know the vacuum structure mostly dominated, as you can see, mostly dominated by this block, which we call the incertons. So if you use the incerton, we should expect that you get some nice structures. So in the future, we can keep calculate some matrix element that people are interested in, and then provide some nice insight for the lattice group or the experiment group that to see what the result they should expect. Okay, so thank you for everyone.
Simon, the Simon in that is the same Simon as the Simon you had lunch at today. We have time for a quick question if someone has one. Or,
yes, please.
Very, very nice one. Thank you for the presentation. It's very cool to meet this, but I don't understand anything.
Okay.
So you're talking about an effective theory, and how do these instanton emerge? When you, I guess you integrate degrees of freedom, and in the end you get the instant. What do they look like? What are they? Can you?
So mostly it looked like a spherical shape. So that's why we define the size by the radius of the free. And how do we get these structures analytically?
Yes.
By solving the Yang-Mills equation. They have a classical solution, which is exact.
Okay. Okay.
And you might ask why we solve the classical solution, because we know the vacuum structure, mostly they are classical solutions.
Yes.
Yeah, so.
Okay, that makes sense. Thank you very much.
Very good. Let's thank again. So, Juan Jose, so. Where is he?
Hello, everyone. My name is Juan Jose, and I will talk to you about a bit about my PhD work with quantum computers and trying to simulate, among other things, fermentation functions. Okay. So this is a general scattering event, and it can be divided roughly in 3 areas. One will be perturbative QCD, which is the hard scale, which we can apply factorization to and separate it to the long distance physics that are encoded, for example, in PDF, in parton distribution functions that are telling us how the partons are distributing between the hadrons that collide. So there in this picture will be this proton here and proton there, okay? And then we have another functions that are telling us how the produce partons in the collision, the hard collisions, produce the hadrons that we measure at the final state. Those are the fragmentation functions. And here in the parton model, we can write them as amplitudes between the parton that is producing the hard scattering, that will be this part, and the hadron that we measure in the asymptotic feature in the light cone. So that's why we have this is telling us that this is a dynamical quantity. So this cannot be in principle treated in the lattice because of this out. Okay, this have to be, they are defining different light cone times. We have here, and this depends, like the PDF depend on X, these fragmentation functions depend on Z, that is the plus momentum fraction of the hadron to the initial parton. Okay, so and we see here some examples of fragmentation functions that are obtained with a global fit, a recent global fit. And we see that in the low Z region, we have huge uncertainties for some fragmentation functions. For example, for the kaon coming from a B quark, also for the eta meson coming from gluons. So we see that we need to improve this. And well, the idea is to try to calculate this on a quantum computer, which is, well, not easy, of course. But okay, so to simulate this time evolution on a quantum computer, we need a Hamiltonian. As we're working on light from coordinates, we need the light from Hamiltonian, which is obtained taking the Electron gauge, A plus equal to 0, and then making a Legendre transform. And this is what we obtain. This is the Hamiltonian, okay? This is the kinetic term for fermions and gluons. here is the interaction between the gluon field and the quark current. And here we see some self-interaction among gluons and other things that came because in this gauge, you can write the A minus component of the field as function of the quark fields and the remaining components of the A field, and these interactions are obtained from that. So to codify this Hamiltonian, because we have to somehow translate this to a quantum memory, we expand the fields in terms of creation and annihilation operators in plane waves. So we can define these cells one particle states. And how we do encode, well, importantly, these creation and annihilation operators satisfy the canonical commutation relations. Okay, so how can we codify these terms in a quantum computer? Well, we count the states that a single particle can have in a given discretization. And then we assigned a sufficient amount of qubits. With n qubits, you can write as 2 to the n binary numbers, and that you map each binary number, you map to a figure here, in which we have like 3 qubits for color, because we have the state of color. This should be 1 bit, but I use this figure for other things. So yeah, this should be 1 qubit because in light from gluons only have 2 polarizations. And then some for momenta. This can vary from codification to codification. And then if you want to represent 2 particles, well, you have to multiply the number of qubits by 2. Okay. We also have this auxiliary qubit, if you want, which is very handy for doing controls and things on the memory. So, well, this is kind of the interactions that the Hamiltonian that we can encounter in the Hamiltonian. We see here the mixing between different Fock sectors. So, for example, from a gluon, we can end with 3 gluons. Okay, with 3 gluons, we can end with 5 gluons. So this is telling us how the different Fock sectors are mixed. And okay, so we have defined these registers for 1 particle, and then we initiate these registers. We say that we store a particle in the register, just changing the numbers. So here initially it will be in a standard state or zeros, and then we apply these operators that can be written easily in a quantum memory, okay? And yeah, we set it to some numbers that we have previously defined. So for example, to encode a particle with momentum 4 and color 1 and spin 3, well, we will write a 1 in color and 3 in momentum and so on, okay? And also changing this to 1, because that is telling us that the register is active and is storing a particle. And then we have a problem that we have to define a state of several particles. Okay, so we can imagine that our quantum memory is a bookshelf, and we want to put particles on there. Okay, so we will start with 1 particle in the down shelf, and we put the second in order. So in the second shelf, not in the third. Okay, so yeah, we have to define somehow how the memory is filled, and we define it to do in this way. So further, we only interpret this as currently filled, and this will be a state that we cannot interpret, okay? And also we have, to antisymmetrize the memory. This will be a quantum bookshelf because our particles are in superpositions, okay? So if you measure the first shelf, you will find a particle that has, quantum numbers of index 2 and quantum number of index 1, okay? And we write those operators like this. So these are projectors that are telling us where we have to put the box in the memory, and these are telling us if we have to symmetrize or desymmetrize the particles. And then importantly, with this expression, we can check that we satisfy the canonical commutation. up to a term that appears when your memory is full. So when you have created a third particle, you can create more. So that will have an impact on your commutation relations. So with this expression, we can, for example, exponentiate these terms of the Hamiltonian here that are creating here a gluon and here creating a pair for the gluon. And we can see the evolution with, so we implement this operator on a quantum memory. We start with a state with no gluons, and then we let it evolve. And we see that gluons start to appear at time past when we apply this operator. We see here that we, since our memory have a fixed amount of particles, we have errors when, for a certain time on, we cannot get the correct evolution because our particles are finite, or the amount of particles that we can apply. So here we see the same idea. So we delete the memory. We apply this operator again and again for this term here. And with that, an image of a meson, very rough meson. This will be the wave function of the meson. Okay, so we have only momentum up to 5. These are the first number is the momentum, so it always sums to 5. And then we have the color, which is 2, 1, 1, 2, 1, 1, 2, 2, okay? And the spin that will always 1. And we can let the memory evolve and measure the probability of obtaining this meson, okay? And this is what we obtain, which, of course, we are doing very small simulations, so this depends strongly on the time that we are taking on our evolution. We have here a source of systematic error in our simulation. But yeah, to improve this, we should have more particles, and you can do that in a simulator. Because these are all are simulator results. So yeah, that's all. Thank you.
No problem. Questions?
Can you compare the performance of the results that you get from your analysis to things that have been measured by experiment?
Not yet.
Okay.
Because this is a very coarse, this is like a proof of concept.
I see, okay, fair enough.
Yeah. This is for a memory of only, I think, you're seeing that you only have here 4 states of momentum on your particles. So it's a very coarse lattice. So, yeah.
So are you ready? I know like when the IBM quantum one, they have a simulator and also you can run it. So are these simulations or also are you also running on real?
No, this is not real.
So you're getting ready and then you'll run it on that.
Yeah.
Okay. All right. Yeah. Just other questions? Okay, let's take one again. So good. Okay, so Diana, all right. Yeah, the top one is the pointer and then forward and back. Is that? Back it up, Carol, back up. Yeah.
Okay. Hello, everybody. I'm going to talk about part of the work that we are doing in the HEP phenomenology group in UAP in Mexico, and it's called the non-extensive description of the charged particle production in deep collisions. So under the string fragmentation model, the particle production can be described through the Stringer mechanism. The Stringer mechanisms give us the probability to observe a particle with transfer momentum PT coming from the fragmentation of a string with tension x squared. In this context, the tension x squared represents the intensity of the color interaction among the colliding partons, right? So initially, this string tension was considered as a constant, but later Vialas proposed that the string tension may fluctuate. So in order to take into account these string tension fluctuations, the PT spectrum must be computed as the convolution of the Schwinger mechanism with a distribution describing such string tension fluctuations. Well, so in the literature, it is usual to find that the string tension fluctuations are considered as a Gaussian distribution. So when we convolute the Gaussian string tension fluctuations with the Schwinger mechanism, we obtain a thermal distribution to describe the PT spectrum. But when we compare with the experimental data, or as we can observe in this plot, for charged particle production from MVP collisions, for data for Rick, for Alice, a different center of mass energies, we can observe how this thermal distribution only fits a low PT regime. However, for high PT values, it considerably deviates from the experimental data. So in order to take into account these deviations, we must enhance the probability of having higher tensions. And we can do this by considering now Q-Gaussian string tension fluctuations. And this is important because Q-Gaussian is a widely used function. It's a heavy-tailed function. It means that it can describe rare events. And also, these Q-Gaussian fluctuations includes a new parameter. The Q parameter represents how much we are deviating from the thermal behavior. So when we convolute now the Q-Gaussian string tension fluctuation with the Schwinger mechanism, the PT spectrum can describe through a trichomace function, which is defined through this U function. And we can observe here for the same data samples that we can now reproduce the both asymptotic behaviors for the PT spectrum. It means for low PT values, we can reproduce the exponential decay. And for high PT values, we can reproduce the power law behavior. And it is very important that when we derive the mean PT, we need the mid PT converge. So that constrains the values that Q can take. So in our model, Q is between 1 and 1.5. So when Q is equal to 1, we recover the Gaussian fluctuations and then the thermal distribution. But this is important because we are finding Q values higher than 1. So this means that we are having systems away from thermal behavior. Well, also in the literature, we can find other approaches such as the QCD-based Hagedorn function that also can reproduce the entire PT spectrum. But remember, our approach is based on the string fragmentation model. So one of the questions that we work is this: is the Hagedorn function in agreement with the fragmentation model? It means can the Hagedorn function be expressed as a convolution of the Schwinger mechanisms with a distribution describing the string tension fluctuations? And the answer is yes. We have found that this distribution can be understood as a string tension fluctuations. And when we convolute with the Schwinger mechanism, we obtain the Hagedorn function. And a very interesting thing that we have found is that this distribution is a heavy-tailed distribution too, such as in the case of the Q-Gaussian. In fact, both distributions, the string tension fluctuation for the Q-Gaussian and the one derived for Hagedorn function are phenomenologically equivalent. Here in this plot, we show the string tension fluctuations for different center of mass energies, and we can observe here in the blue and green curves that they behave very, very similar. So as I mentioned, these distributions are heavy-tailed, so they are enhancing the probability of having strings with higher tensions, and in consequence, we are enhancing the probability of having high PT values. So that's why these approaches can describe the high PT values, and notice that here that the Gaussian, the thermal distribution can describe this region because of the Gaussian string tension fluctuations. They are in red, right? So one of the main results of our work is that heavy Taylor distribution are very important to describe the particle production. But now, if we are talking about a system that departures from the thermal behavior, we can expect that there be thermal fluctuations or temperature fluctuations. And in this context, the temperature fluctuations for our approach can be understood that the system has small regions with different temperatures. In contrast with the thermal distribution, which is defined through Dirac deltas, and this can be understood that the system created has the same temperature along all the system. So, well, to summarize, our main research is by considering heavy Taylor string tension fluctuations. In consequence, we are having now a non-extensive particle production, which leads us to a non-thermal description of the system. From there, we have derived the temperature fluctuations, but also we have derived some thermal statistics for the PT spectrum, such as the Shannon entropy and the heat capacity. And thank you.
I have I guess, questions, because more general, because when I think of maybe naively, when I think of a thermal production, I think more QGP, and because then, like the soup, everything's there, and then you get these like the same tails, but in PP, I don't think thermal means coalescence or QGP necessarily, right? So I guess what do you mean by the thermal like? Is it just a tail or?
Yes, that the experimental data don't behave as this exponential decay. Remember that this thermal behavior is very similar to the Boltzmann distribution. And here we can observe how the data doesn't fit to this exponential decay. So that means it's not thermal. It's not in that sense a thermal equilibrium. But this is the temperature of the system created, not of the medium, like that.
Okay, see. And then from this, does it help like pin down and understand hadronization better? Because that's one of the big question marks that it comes down to how we end up getting the particles, or not quite, or?
Yeah, we can extract a lot of information from fitting the experimental data. And yeah, as in one of our works, we for instance, for each data sample, we fit the data and we obtain a Q and a sigma parameter. So with all that information, we have a result of a phase transition in terms of the Q and sigma parameters, and we can predict the QGP. We can expect the QGP formation or not expect the QGP formation for some Q and sigma values. But
so I mean, the Q equals 1 gets you the Gaussian, and then basically in your fit, I assume you just sort of step it up.
Yes, we have increasing Q values as the center of mass energy.
Yeah. And then coming back to the other question, I'm thinking this in terms of parton models, what I'm used to. So the high PT, we calculate a higher order, and that comes from a single heart emission. Yes. But out at there, what you can get is if you have basically extra effects, soft gluons or other stuff in there, or initial KT, that smears your distribution. And I mean, that's a look at the scale, that's a log walk plot. So even a little bit of smearing will put it out. So in some sense, is that the kind of thing this is sort of modeling? Is that a fair assessment?
Yes, our approach is a mean field approach. So it means that we are considering all these contributions by modeling it as a rare event. So in that sense is that we can describe all these high PT particles.
Other questions? Now let's thank Dan again. Bjorn, go ahead, sir.
Just to that point, so you're saying I mean, the jets should come with like a power law spectrum just from PQCD, right? But you kind of include those effectively then with this function? Is that what you do?
Can we sorry?
So you're not computing the jet spectrum, right? I mean, you could compute the high PT partons, right? They would come with like some power law distribution, right? Just from QCD. But in your case, you're not putting that in, but you're just explaining that part effectively, I guess.
Yeah, that's okay. Yeah, and well, these results are for the case of PP collisions, and we also have some results for heavy ion collisions, and we have to include other or effects that emerge in that kind of collisions.
Good. Thank you again. Jan, do you have your slide? Did you send them to me?
I send you by mail.
Okay, sorry. Just a sec. Sorry, I did a last minute shuffle on this. That looks better. Sorry, let me actually download it properly. Got that, and it should be sent. All right, very good. Yeah, top one is the pointer, and then forward and back. Okay, all right.
So good afternoon, everybody. And so today we're going to talk about electric gauge boson production, electric collisions at Ford rapidity. So in order to initiate the talk, we must recap a little bit and put in our minds the lecture of Sturman about factorization, and also the last talk about the small wax physics. So why we are looking for the electric gauge boson production, especially in Hadronic collisions, because with the Herrera shutdown and the IC as a proposition to the future, how to access a small physics region? Well, inside the Hadronic collisions, the electric gauge boson must be a good proof because of the clean final state, because there is no polarized, right? So we can analyze better the initial state wave function, and especially at Ford rapidity. Why Ford rapidity? Because the usual way to approach this kind of process of a PP collision going to a dilepton from this electric gauge boson production, and if you want to analyze the jet or not, this is your choice. But usually we use this in the collinear factorization approach. And in the collinear factorization approach, the partons inside the proton are in the collinear, distributing the longitudinal momentum. However, in the Ford rapidity, I assume that everybody knows how we can correlate the rapidity with the angle. So, okay, let's move forward. And we can connect the the value of the rapidity with the fraction of momentum carried by the parton of the projectile parton and the target proton. So for the rapidity, this value is going to be high enough. Therefore, one of the protons is going to be very diluted and the other one is going to be very dense. Therefore, we expect a violation of the collinear factorization. So a bunch of groups have proposed different factorization schemes to deal with this kind of things, or just deal with the violation of the collinear factorization. One of the hybrid factorization proposition is this one called the color-dipole asymmetrics framework, where given the kinematic and the dynamics of on each one of the protons, we have the projectile. You can see like a projectile proton with a dilute system interact with a target proton is very dense, and this interaction is going to be represented by the projectile proton PDF acting convoluted with the parton target cross section. So we have a proton, and this proton tag a parton with the dilute system, and this parton, a quark, is going to interact with this dense system, and all this dynamic is going to be written by to be encoded inside the parton target cross section. And of course, this is just fragmentation as you wish. So we think this parton, the color-dipole asymmetric framework, the parton target cross section, that is where our ignorance about the dynamics of the system is. In the most general form, it is written this way. It was proposed by Nikolaev, Wolfgang Schäfer, and Zakharov in a series of papers in the beginning of the 2000 years. They proposed this framework for a generic A going to B and C partons. So they are analyzing colorized objects. But in our case, we propose to extend this for a work when one of these final state guys from this emission is a Electroweak boson. Therefore, we have a quark, and this quark is going to radiate Electroweak boson and can or not change its flavor, because if it's a W, you change its flavor. Therefore, when we have this case, we have a simplification of this function, of this old equation, because this 4-point correlation asymmetric object is going to be simplified as 2.1. And from the optic theorem, we can just correlate with the dipole cross section, which is model dependent. Therefore, in order to evaluate the electric gauge boson production in hadronic collisions at for the rapidities, we just need to the PDF, which is given by the CTEC, for example, collaboration, and evaluate this parton target function, which depends on the color dipole element, which is model dependent. Therefore, the only analytic ingredient that's missing is the wave function, and it's present in the literature for the photon and for the Z, but not for the W. So our work was to extend this. This was present in this JHAB paper that we published last year. So what was we like create a effective vertex, not the proper way to say it, but it's a vertex when we can englobe the production of any electroweak boson. So it's just do the math, and so we are able to construct the 4 wave functions for the transverse longitudinal contribution, for the vector and axial contribution, y-axial contribution, because now we have a Z and a W, and they have parity, right? So now that we have the light front wave functions, it's plain simple. We can construct the parton level cross sections, right? So it's just convoluted with the PDF, and we have, for example, just the electroweak gauge boson production. And of course, our main results that now we present a generalized description for our electroweak gauge boson production, and you can just use this in the momentum frame or in the back parameter. Is just a Fourier transform difference. And most recently, in this year, we extended this when we tagged the jets associated with this electroweak gauge boson. And in order to do the math, it's just consider this one. In the other case, we didn't disregard the integrated over this because we are not interested in the jet. Okay, so once more we are able to present a generalized expressions for the parton level, and in our main results at first time we are able to present the W plus and minus production or predict that also in the other case, but in this case we can take the jet, so we can, for example, analyze the angle between them. So just to summarize, sorry for the time, I just prepared for a 5 minutes presentation. Sorry, but we can talk later more. I have more slides after that, but just to summarize. So in order to have these formulas to evaluate the electroweak gauge boson production inside the collisions at this further rapidity, we derive for the first time the generic expressions for the light frontal wave functions because it was necessary, right, from the analytic point of view. So we have a vector contribution, axial contribution, and we presented the parton level expressions. And one may ask, and how you know, because I didn't show any graph, how you know that works, or how you know this generalization? Oh, well, from special cases, as I said, we have wave functions for the photon and the z. So if we have wave functions, we have the parton level cross sections, right? And from our generalized expression, if you constrain for the photon or for the z, we have the same expressions on the previous papers in the literature. So that's the reason we know. And of course, as the moving forward is just now do the phenomenological analysis and compare to data, right? Unfortunately, we didn't have the time yet. We are looking for other theoretical work within this formalism. And this is all that I have to say today. Thank you.
Questions?
Sorry, this is very naive and probably you said it. I just wasn't able to hear you. I'm a little bit hard of hearing. I'm sorry. But can you explain to me again why the collinear factorization fails in the particular case that you presented us?
I'll move forward to explain at the second slide.
Okay.
Because of this. Because of this. This said before, but in the morning, we have the picture of the structure of the proton, right? Oh, sorry, I didn't know what I did. I don't know what I did. Okay, this is not. So we have we can look at these two images, right? This one gives the evolution, right? If we go forward in the key 2, we have like a better resolution of the proton. If we go to evolve in the rapidity or assess the small x region, we're gonna see that inside is more populated. Is the crowd party. And this is the PDF object that you can see from the X sphere, for example. This is with Herrera data, right? So what we know that for the proton, for example, we have the 0.6 U quarks and D quarks, but with a huge amount of. So they are the valence quarks. But if you go to the smaller X, it's highly populated by gluons. Gluons that has just a little tiny part of the momentum. Okay, why I'm saying this? Because the collinear factorization and the evolution of the Diglap equation are linear effects. So when you use, for example, the Diglap is going to evolve this way, right? And the BF is going to evolve this way. But they are linear. They are predicted that 1 goes to 2. However, in this kind of vision, no linear effects must be taken account, like a combination, as said in the morning. Therefore, that collinear factorization that does take account the PDF that's linear should not be the best. I'm not saying that it breaks off. We expect that it breaks off. That's from my understanding. Maybe I'm.
If I could just add, I mean, one thing you could do is sort of do a resummation there. And in fact, one of the exercises that the XFitter is they implemented the Hell code, which high energy waiting log, which resums that, and so attempts to push farther in that region. So these are the kind of effects that you have to worry about. Yeah, exactly.
That's correct. I missed the region in which you were the regime that you were talking about. But yeah, okay. No. Now it's clear.
Okay.
one more each.
Okay. What experiment are you thinking? Like, what's your rapidity?
Sorry?
What eta are you thinking of? What's your eta for
Okay. We know that that is LHCb data,
okay,
like between 2 and 4 rapidity. Usually, I can't remember the.
Are you doing, if you're doing jets, I feel like, I think CMS and Atlas have really like, are able to go really forward too.
Yeah, I would need to get that up.
That's on and all speakers good. Let's break till a quarter after. We'll have some coffee, and then we have 4 more talks, and then you guys can help chop and prepare for the barbecue. So yeah, we'll see you in about 15, 20 minutes. And I'll upload the next set.
Watch. Heavy. But I mean,
Okay, so welcome back and to the final session of the week. It's been a busy week, but yeah, seemed to have held with it. But we've got a final round of talks. And so Sanskriti will tell us about some of her work. So we'll start with you.
I'm Sanskriti from India, and I mainly work in small x sector of QCD, especially dealing with various evolution equations. I want to start with something that we have been seeing for the past few days, these type of structures. These are basically the correlators of gluons. What they do is they just correlate different states of gluon, like from final to initial. And if we parameterize these correlators, we are left with these GTMDs. So what are GTMDs? GTMDs are generalized transverse momentum distributions. And you may ask how they are different from TMDs. So GTMDs has an extra parameter, this right over here, delta, this delta dependence. And this delta, I don't know if this is visible, this is delta. So you can see in this correlator, the initial momentum is not same as the final momentum. And the difference of the two gives us the delta. And delta, we can have 2 types of delta in the longitudinal direction and in the transverse direction. So here, what with the delta that I'm talking about is the transverse. So you may ask that how these GTMDs are important. So what happens are like there are 2 types of processes. In an interaction, the particle can either flip their spin or not. So these spin flip processes are often considered to be small, like they are not considered to be important at small x physics. That is because they were thought to be suppressed. But recently, Yoshitaka in his paper showed that these spin flip processes also follow exhibits the Reggie behavior. So they can't be, ignored in the small x regime. And these GTMDs are actually directly related to the spin flip processes. So we need to study them as well. Among these 4 GTMDs, the F11 and F14, they were well studied, well documented. But these F12 and F13, they were always neglected, expecting that they'll just die out in small x. But I promise I'm going to show that they will not die out and they actually survive in the small x. So Yoshitaka in his recent work actually gave the evolution equations for these 2 GTMDs, F12 and F13, which looks like this. It does look like somewhat similar to BFKL, but it is exactly not BFKL. We have some extra terms over here. So in my first work, I analytically solved this evolution equation. And for that, I assumed the structure of this F12 of this form, that it has some X dependence, which is Bjorken variable, transverse momentum dependence, and this phi dependence. The phi is the angle between delta and K. I took the inverse Mellin transform of F12 and I am left with the final expression for F12. So what we do to solve these type of evolution equations is just assume a solution, put back into the solution, get the eigenvalues, and you're done. It's easy. Not quite, but yeah, this is the procedure. So what happens is, if you get the eigenvalues, I don't know if it's visible, you just need to put back into the expression here to the power of 1 by x. And you get a long series solution. So for BFKL, standard BFKL, what happens is the only surviving solution corresponds to the mode n equal to 0. And here we can see that it is well above the sea. And it is like actually surviving. But my poor solution, it is just this much, barely surviving. But here it's there. It's there. So this looks like this. The solution looks like this. And the power, so what happens is x is a very small number. We know that. That's why we are here. But what happens is if I take 1 by x, it suddenly becomes a large number. And only positive values of a large number will survive in small x. So these powers of 1 by x needs to be positive. And only the power corresponding to the mode n equal to 2 was actually positive. This will lead, this will govern the leading behavior for F12 at small x. And it is supposed to increase at small x, which was earlier supposed to be ignored. And this, the mode corresponding to n equal to 2 will lead to an explicit phi dependence, which was actually not present for the standard BFKL. And now you may ask, what are the what are the procedure where you can see F12? But to be honest, we don't know. We don't know because F12 has been ignored for its life, and we gave some importance to F12 and hence the solution. So this is also a picture that we saw today, and I actually stole it from there, from presentation. So this is the dipole picture. So in the dipole picture, what happens is in like a standard DIS, the incoming photon actually breaks into quark-anti-quark pair. And this quark-anti-quark pair is supposed to interact with the hadron. But the interesting point here is if I take this position to be X and this position to be Y, and if I switch it, nothing happens. There is a translation symmetry. So, but there's a very important significance of this translation symmetry. The dependence on X and Y of the scattering amplitudes now just reduces through X minus Y. You don't need to study anything else. You just need X and Y. That's it. But as I was talking to some of you and I was telling that I like to do things in the momentum space. So I was thinking, hey, what is the conjugate in the momentum space? I was researching what happens in the momentum space if I apply the same transition, but nothing came up. So I came up with the solution. So I studied the equivalent proposition of this translation symmetry in the momentum space. And I actually got a quite interesting result. We were able to show that we can actually study the off-forward evolution through the evolution of two forward scattering amplitudes at two very specific momentum. So yeah, the evolution of GTMDs, which was earlier quite difficult to get, now we can directly get the evolution of two TMDs, two very specific TMDs, and then we can see how GTMDs will evolve at small x. The same argument we also apply to the Odderons. So Odderons are basically C or 3 gluon state, which are expected to be present in only delta not equal to 0 momentum. And here we can see that if we put delta equal to 0 in this equation, the evolution of Odderon will eventually die out, which is actually expected from the experimental results as well. And thus, we can say that Odderons are more likely to be found in the non-forward scatterings. So to conclude my entire talk, this data is really important. Thank you.
With this and see all connected with the morning lectures there. We have time for questions.
I'm not sure, but two things. One about this in the start, the structure functions, the one in 20.
No, there are no structure functions. Let me just go back.
The first page.
This one?
Sorry?
This one?
No, later. This one.
Okay.
Yeah, it's the same. The one we showed.
This one?
Yes.
Okay.
Not this one, if you show this one. We have a calligraph.
This
one? No.
Sorry, I'm not able to understand. Sorry. Yeah.
This one, but okay, not it's in this is a differential equation, right? Yes.
Yeah, this is
No,
integral differential equation. Yeah.
Right? Yeah. Is this somehow, can you have any connection?
Yeah, that's what I said, that F12 has been ignored up till now, and we actually don't know any observable for F12, and that is actually a challenge. And so, yeah, we don't know any observable for F12 as of now.
Yeah, okay. Next page. Again, sorry.
Okay.
It was very dense.
Oh, yeah, sorry.
No, not sorry. Yeah, this at some point you had this as model dependence, and maybe based on this, this leads you to something where you have anything from this, or it was just mathematical. This harmonic, you have some harmonics at some point. This cosine.
Yeah. Like in the last slide. Yeah, this one.
Yes.
Yeah. No. Actually, we took this in the inverse transform over X, and if we take the inverse Mellin transform, then we get an continuous.
No, I asked if it's somehow physically intuitive because we have some harmonic.
The summation over n.
No, you have the cosine there.
Sorry,
we haven't
able to understand.
Can I let's say that for the barbecue. Are there other questions? Yeah.
So when you include this all forward parts, right? Aren't you assuming that there's some? So if we go back to position space, are you assuming then the parton moves as it goes through the shock wave? Yeah. If I have this off forward phase, I mean that momentum is conjugate to something, some transverse separation.
Yeah. Actually, what happens is the K is conjugate to this R, and delta is conjugate to the impact parameter B, which is X plus Y by 2.
Right. So, I see. You have the dipole. Right.
Yeah,
so you're still assuming that the parts.
Yeah.
Let's thanks Sanskriti again. So.
I know what I was gonna have too, because I was like, okay, the transverse size isn't supposed to change. See, it's twist up my phone.
Right.
No, that wouldn't right.
Sorry, I have to reload that one.
Right.
So to choose.
So
That's free.
The impact parameter changing, both of them are changing.
Yeah, but it just says that the dipole mechanism. This is
Yeah,
just.
top one's your pointer, then
As long as
forward
they-
and back. Okay. All right.
But I see what you mean, the at change itself and also symbols.
Hello, thank you for the opportunity to be here. I'm Alan Hernández from Mexico. I don't work in QCD, I work more on electroweak physics. And I would like to tell you about my research. The name of the presentation, the title of the presentation is CP violation in Higgs decays. And the motivation of this work is that 2 years ago, the LHC reported for the first time the first evidence of a C boson and a photon produced through a Higgs boson. As we can see here in the original paper, here, we can find that it says the measured signal yield is 2 times the standard model prediction. What's the meaning of the measured axis of the signal that they observed at the LHC? Well, the signal, is defined as the ratio between the between the okay, yeah. The signal is defined as the ratio between between what they observe in the experiment, this part, and the standard model prediction. They observed 2 times. The signal is 2 times the standard model prediction, and this result agrees with the standard model at 2 sigma. But we are trying to be optimistic, and we think or we believe that this result can be explained through new physics. The question is, what is the new physics? What is the CP violation? I don't expect new physics through the Higgs production. That's because the Higgs production is well understood. It is well measured, and it agrees with standard model prediction, which corresponds to a Higgs produced through a quark loop, a top quark loop, and as we don't expect the new physics from the Higgs production, the signal can be defined only as the ratio between the observed branching fraction and the standard model branching fraction. And a lot of models are trying to explain this result. For instance, two Higgs double models, multi-symmetric models, left-right models with new particles. But what we are trying to explain here through CP violation is this result. The question now is, how can we introduce the CP violation in this process? I can describe the process through the following effective Lagrangian. H1, it can be described, in terms of 3 form factors, H1, H2, and H3. H1 and H2 are related because of gauge invariance. And at the end, I only have 2 form factors. In the standard model, the form factor H2 or H1, it is of order 10 to the minus 1, and it is well known that this is a complex form factor. The form factor H3, it is related to CP violation, and it is 0 in the standard model. It cannot be induced in the standard model. The next question is, then we can assume that the form factor H3 is different of 0, and we can compute the correction to the signal observed at LHC. And here, this delta gamma represents the contribution of the CP violating form factor. And using the results from the LHC, we have obtained bounds for the Fritz times for for the H3 form factor, which again is related to CP violation. The results are the first bond obtained through experimental data for this form factor. And well, I didn't mention, but why is the CP violation important? Well, as you know, a certain amount of CP violation is necessary to explain the invariance between matter and antimatter in the universe. In the standard model, we have CP violation through the CKN matrix, but it is not enough to explain the invariance between matter and antimatter in the universe. So we require new sources of CP violation. What we are proposing here is that a new source of CP violation can be induced in this vertex. Well, the next question is it possible to induce this form factor? Well, we are also proposing a new extension, a generic extension of the standard model, where we include flavor changing neutral currents mediated by the C boson and the Higgs boson. This kind of couplings doesn't exist in the standard model, and through this effective Lagrangian, I can obtain the following Feynman diagram at the one loop level. You can note that we have flavor violation in this vertex and also here. And well, I can also compute the correction. I can compute the Feynman diagram, and I can find that if I include that effective Lagrangian, I can induce the CP violating term, which again, it is not possible to induce it in the standard model. We can use limits on flavor changing neutral currents, current couplings of the top quark. We expect the more relevant results from top quarks running into the loop. And well, we can find that if we use the results, we estimate a value of 10 to minus 5 for the H3 form factor, which, as you can see, is very small. If we compare with the limits that may explain the excess observed at the LHC, they are very small. But well, we also explored the possibility of a new family of quarks and in this case, it's possible to explain the result observed at the LHC. I just want to say that the LHC also reported 3 years ago the first evidence of two C bosons produced through an off-shell Higgs boson. And well, if we also consider, if we also parameterize the Higgs boson coupling with 2 C bosons, and we include a CP violating term, we can also use the same effective Lagrangian. We can find contributions to the H3 form factors, which again is CP violating, and we can estimate some values. And the interesting thing is that the effects of the CP violating form factors are difficult to observe on the unpolarized process. But if I consider the polarization of the C bosons, I can define a new kind of left-right asymmetry, which we are also proposing for the first time. And we find that it can be written in this form. Please note that here we have the CP violating form factor. And if we can observe if we observe this asymmetry at the LHC, it will be a signal of a new source of CP violation, which again is necessary to explain the invariance between matter and antimatter in the universe. Well, effects of new physics are still possible in Higgs coupling. The CP violation can explain the excess observed at the LHC, and new sources of CP violation are possible in Higgs couplings with the C boson and the W boson. And well, thank you.
So, I mean, it's an interesting process because, for example, the gluon, you've got a fermion loop in there, and typically it's dominated by the top quark, the heaviest. So here, I mean, you're looking for flavor changing. Presumably, I mean, the Higgs coupling is also proportional mass. So again, if you have something funny going on in the heaviest generation, you'd be sensitive to things like that. So, yeah, that seems like an interesting channel to look at, though. So.
Yeah, it's very difficult to observe this kind of process, but we are trying to find some observables.
Mm-hmm.
You can measure the CP viability contribution.
Yes, I mean, they got the the ZZ now, the Z photon is see these different branches just come out. Question here?
Like how much CP violation does this introduce compared to what's already in the standard?
It's not too much. We also require more. We still require more sources of CP violations in order to explain the invariance between matter and antimatter.
What how is there any chance? I mean, I don't know. I'm thinking because these channels are is there any other model that could explain the 2 sigma difference from the standard, like any other besides the CP violation or possible explanations?
Yeah, there are also models trying to explain that result. Models with new particles. It's called two Higgs double models when you can introduce new Higgses and supersymmetric models. Yeah, but there are a lot of models that they are trying to explain.
The run 3 help you?
Yeah, maybe for sure, because they're going to improve that result, and we will see if these results agrees completely with the standard model, or we can confirm new physics.
That's interesting because you have to tweak the Z gamma, but you can't mess up the ZZ at the same time. So it's a delicate balance. Was there a question, Michael? No. All right. Any others? No, let's count again. So. Whoops. Sorry. Okay. All right. All right.
Okay. Thank you for sharing this. Give me the opportunity to present my work. But now we have here a lot of this beautiful object, an elusive object for scientists, specifically for the experimental point of view. So this is my question: is eta C meson production a golden channel for the study of the Odderon? So we must see what happened with this.
Oh, what is? Sorry.
So let's first review a little review for the Odderon. So the Odderon in the pre-QCD era was or is a rigid trajectory with odd charge conjugation parity C -1. So what the people did experimentally, if you have, for example, in one kind of collision, a gluon emission, and then you have a 3 gluon exchange like the Odderon, you have C parity -1 and C parity -1 into the photon, and then you are able to found the meson production. So the counterpart of the Odderon is the Pomeron, which has the charge conjugation +1. So it's a lot of interest at high energy, this object, because in the next section, in the next slide, I will show you what happens. So this is the way how the sharp conjugation works. So is swap into this dipole the transverse coordinate, and you get a minus sign. So with you get this minus sign, you have into the deep in one process, you have a contribution come from the other. Here we have a Cornell-Martin theorem that follow from the Pomeranian theorem. That is, the statement is that at high energy limit, in the rigid limit, the asymptotic region of these two objects asymptotically goes to 1. So naively speaking, we can think that, oh, okay, according to this first statement, the obvious idea is that the difference is 0. That what happened when experimentalists analyzed experimental data, they found that it was a difference, a little difference in the deep region here, for example, and you have some difference, and the people think that this difference could be somehow, and they call the other on this difference. So this is a paper that published experimentalists by this two collaboration, in which they claim that they discovered the other. So you can see here, this is in blue, you have the data from the measurement of the zero collaboration, PP bar, and then the people extrapolated the data from the totem to this energy, and you can see here. But this is a part of the discussion today, a hot discussion today about if the Odderon was discovered. Okay, let's examine briefly what's happened with with this process. So here I put the C parity of this meson, eta C meson, it's +1. So J psi meson is -1. The photon is -1. The Pomeron +1. And the other on -1. So the golden channel to study and discover the Odderon is if you may measure eta C, meson production. So you think, if I have this meson for this meson production, you will find this object. This is the Odderon. So here I took this paper from Dumitru and Stiebel, and they did this. They did some calculation. So here they put the interaction, the exchange of the photon. So you have -1, -1, and you get cierto of the eta C meson. So this is large contribution in this slow T regime. So you are not able to find the Odderon in this regime. But the second one is when you have the Odderon tri-gluon exchange in this part. But approximately when you have T, 1.5 GeV is able to, that you may discover the Odderon if you measure this quantity. And another one that fulfill this statement about the C parity is if you have 2 gluon exchanges plus 1 photon. But you can see here that this contribution is very, very small. So, but what happened? What is our proposal? We propose that this is something new that you have no with a photon emission. So you may see here you have -1, the photon emission -1, and then mediated via Pomeron, and then you can have here eta C production. So this is some kind of background, if you think. So the experimentally have to be careful with this, because this is some kind of process. So here, what we did here, we calculate the first part is the amplitude 1, and the second with this emitted photon before the shock wave, and amplitude 2 is with the emitted photon after the shock wave. So we wanted to calculate it with this formula. And so here you have the cross section, then you have to sum over spins of photons in the final state, and then averaging over elicited in the initial state. So this is the difference. What is the difference between amplitude 1 and amplitude 2 is only the wave function. So this is the last part, wave function of the eta C production that is published in the literature. You can find this, but we have to calculate this new wave function that comes from this photon that you produces this fermion here and the emitted gluon, which lambda and sigma are the elicited of the incoming and produced photon. And these elicity are from quark and antiquark. So this is only the longitudinal, typical longitudinal fraction momentum that carry for the produced particle here. And then you have here, I am working under the CGC approach. I use the BCGC model, and only have you here the Fourier image. So that here, I only wanted to show the magnitude of the calculation, but then, of course, a lot of encoding here, but you can see my paper that I showed you in the first slide with all the calculation. But it's a lot of work and time consuming, especially from computer point of view. But this is the total wave function that you put here. The same to apply this wave function. This wave function here, for example, is different to the first object, and then you have here the quark anti-quark pairs goes to this gamma eta C production. So the same thing here. Our results. What happened with our results? So this is the golden channel that the people have studied. You can see here that goes to have the virtual photon. Then you have the JBSI meson production that decays, the calculation branching radio. But here you have this undetected photon. But all with calculation we thought this with an undetected photon. So what happened here? In order to predict our result to the Electron-Ion collider, the measurements at this energy, we found that the sigma total is 208 femtobarns with this luminosity, instantaneous luminosity. So the production rate is approximately 108 events per day with this quantity of the produced spiral of eta C gamma. But of course, it is very difficult because you are not able to measure directly this part of eta meson gamma. So you have to use the decay. So this is here you have the paper using you need to multiply for this guy with this number, and you get the counting rate approximately to 139 events month with 540 detected event and 100 femtobars minus 1 of integrated luminosity. So here we have large contributor of this channel, and then this is what Dumitru and Stiebel did in 2019. So the contribution, of course, is very small in contrast with the Pomeroy contribution. This is the important point here, that here these two processes are mediated with by Pomeroy contribution. So what happened with the question? We have some hope experimentally. Yes, it is possible to separate different
mechanisms even when the final photon is not detected, imposing appropriate cuts of the variable Q minus delta square. So where Q is the momentum of incoming photon and delta will be the momentum transverse in the recoil product. So this variable, this whole variable correspond to all of which of the first process, the second one, and the last one. And this you may have this one, the experimentalist, to discover the Odderon if you wanted to measure, like Sanskriti said before. No, here Mr. Liu said that you may measure eta C via Odderon. So, but this is very outstanding precision about experimentalists need to do, and consider this this calculation because the eta C production is not sure mediated by the Odderon. You may have one undetected photon that could be produced at eta C via Pomeroy. So that's it.
Yeah, questions, Michael? So, I mean, the T dependence seems crucial there. So can you do that pretty well? Is that feasible?
I'm not experimentalist, but our results coincide with what did Dumitru and Stiebel. And when we show before, so you said here that in this part, Dumitru, you have in Dumitru the photon exchange, and from 1.5, there is possible to discover the Odderon via eta C production. But here we have, this is largely decreased with mediated via Pomeroy. So then start working the Odderon in this part.
Okay, other questions? No, let's thank Michael again. Right.
Hello, I am Nicholas Baldonado, very recently Dr. Nicholas Baldonado. I do research here at New Mexico State University, or there at New Mexico State University, and I mostly study this small x helicity. I've mostly done phenomenology and I guess a little bit of theory. I did not change this presentation at all, so there's way more than 5 to 10 minutes worth, but I'm just going to skip through the highlights, I think. So the first thing, very dense, but a lot of this is stuff that Bjorn already covered this morning, and Yuri will probably cover more of it. And we've already seen a few different spin decompositions. But essentially, we're taking a look at the proton spin puzzle. We know the proton's supposed to be spin 1/2, but we don't exactly know the individual contributions from the quark and gluon spins or the orbital angular momentum of the quarks and gluons. But what we want to take a look at is the Helicity PDFs, which is just like normal PDFs. They typically normal PDFs giving you the distribution of quarks and gluons based on their X momentum fraction and the Q squared. Helicity PDFs do the same thing, except instead of just giving you the distribution of quarks or gluons, it's the distribution of the quark or gluon helicities. And being at small x, we're mostly taking a look at this high energy regime. And that's because you might have seen in Maria's talk, or even in probably other talks that we're going to see later on, the spin contributions usually only go from 1, which is the highest, to some minimum value of x, sometimes 5 times 10 to the negative 3, sometimes 0.05, or somewhere in between there. And that's because x scales with energy. So no particle collider is ever going to probe at x equals 0, but we still want to know what's going on at small x, and thus we're relegated to some kind of theory to describe it. We've already seen a few different versions of this large X picture of deep inelastic scattering. Deep inelastic scattering is usually a pretty easy place to start with small X physics, where we just strike a quark, If the X is large enough, it just kind of looks like a valence quark. But then at small x, we're getting the dipole formalism, where this photon is going to split into a quark-antiquark pair, and that's going to be what's interacting with the proton wave function. The proton itself also becoming a lot more dense in the small x limit. And just like we saw earlier, Bjorn actually had a really good example of this, or a really good picture of this Wilson line, where we have all these essentially like color rotations. You put them all together in an effective vertex, and you call it a Wilson line. The only thing about Wilson lines is that they're eikonal. And while that's really good for whatever you're doing in small x physics, spin or polarized dependent calculations are sub-eikonal in nature. It's a sub-leading effect. It's suppressed by a power of energy. So we can't use typical Wilson lines. So we use a polarized Wilson line. This is something that was actually developed by my collaborators, Yuri and Dan Petoniak and Matt Siebert, my advisor. I'm sure other people have done other work on it too. But it essentially takes a sub-eikonal interaction and inserts it in your Wilson line. And now we have something that is sort of sub-eikonal that's capable of transferring spin information while also being technically a Wilson line. Mostly because it's actually very simple. If you write out one example of them, there's a whole lot of ways you could write this kind of interaction. It essentially just looks like a Wilson line with a sub-eikonal vertex sandwiched in between another Wilson line. And thus, when we have a dipole formalism, which is just a combination of Wilson lines, a polarized dipole is going to be a combination of an unpolarized and a polarized Wilson line. And, oh, I pressed the wrong button. Oh, it didn't do anything anyway. So that's all good. But that only tells us a small x picture of something like DIS. We are interested in the small x evolution. We want to know what the PDFs look like as x decreases, because we can only get some larger x picture from data. So how are we supposed to know what's going on at small x? Well, via typical evolution equation, something that we've seen before. This picture is actually very similar to one that you've probably seen if you were looking up BFKL or BK evolution, I suppose, where we essentially take a dipole and then we want to take a look at these radiative corrections. In this case, we're looking at radiating gluons, but the effect is still the same, where we want to pull out specific corrections that are enhanced in the small x limit. And I think George Sturman said it earlier this week, radiative corrections eventually gives you resummation, which is summing up all of these radiative corrections. Resummation begets evolution. And in the case of BK or BFKL, or I'm going to say BFKL for sure, the small x evolution is single logarithmic. So all of these diagrams, you resum them all together, and you get an alpha s times the natural log of 1 over x. However, in the polarized case, because of that sub-eikonal vertex, we actually get a double logarithmic approximation, where polarized dipoles evolve with an alpha s and 2 logs of x. And that's very important because as x gets small, this resummation parameter is much bigger than this one, meaning we could see some sort of small x effects earlier in polarized observables than we see in unpolarized observables. And this is just a whole lot of math. These are what the polarized dipole evolution equations look like. I haven't taken a very long look at all of the other ones, all the unpolarized cases, but I don't think they look like a big set like this. Maybe they do. They don't. But essentially, the cool things about this is that, one, they're linear. We have a whole bunch of different polarized dipole amplitudes, and they're all coupled together in all of these equations, but they're linear. We have a few different definitions. QF for up, down, and strange. G2 is a gluon type dipole amplitude. G tilde, which you'll see right here, is another gluon type dipole amplitude. And there's a few neighbor dipoles that are just used for resummation. But essentially, these evolution equations have a few main properties. They're linear, meaning we don't see products of dipoles. They're coupled, so they all interact with each other. And they're closed, which means you could actually solve them, numerically at least. Other work has been done by Jeremy Borden to solve them analytically, whether in the large NC or the large NC and NF limit. These don't close on their own. They're closed in the large NC or large NF limit, where the number of colors or flavors is assumed to be large just to make the math easier. And the really cool thing about these evolution equations, just like we've seen in other types of factorizations, we can actually write our observables or our HPDFs in terms of these dipole scattering amplitudes. We saw stuff like the unpolarized PDFs written in terms of dipoles. HPDFs can be written in terms of polarized dipoles. So then we have a very easy through line. If we know how to evolve these polarized dipoles like we do, well, that means that we know how to evolve the HPDFs. So really all we need is a large-ish or maybe small-ish initial condition for the Helicity PDFs, and then we could use the evolution equations to evolve them and take a look at what the HPDFs look like at small x in a very similar way as they do for the DGLEP evolution equations. Bjorn had a really good depiction of something like the small x regime and then the large x regime, and as you evolve in Q-squared, you can kind of probe into it. Same thing happens in small x. So something that was once non-perturbative, you can calculate at least a part of it in a perturbative sense. And then we do phenomenology, which is essentially to say that we do some kind of Monte Carlo sampling of all of those initial conditions that I mentioned before. They're just written here as, Q naught, G tilde naught, stuff like that. We parameterize them because at Born level, they look kind of like a combination of some logarithmic variables, which we just renamed eta and S10. So we give each of them some 3 parameters to make it nice and flexible, but not too flexible. And then we randomly sample, oh, I pressed the wrong button again. We randomly sample these A's, B's, and C's, solve the evolution equations for any given initial condition, and then use those A's, B's, and C's to just linearly combine them. We know we did a good job when we essentially get a uniform distribution of our parameters over some small parameter range space. We know that we've constrained those parameters, and we know that we constrain them well if we compare them to data, and we do a good job, which in this case, we're fitting to DIS and CITIS data. In total, for DIS and CITIS, there's 226 data points, and we define them all with a pretty good chi-squared, very close to 1. And this is actually a couple phenomenologies ago, where we only had DIS and CITIS data. This gave us some pretty good answers. One, I don't remember, I think it was Martha, I can't remember exactly who said that with semi-inclusive scattering processes, you could get flavor separation in your PDFs or HPDFs. That's what we saw here. We were actually able to resolve delta U and delta U bar along with the strange and the down quarks. But one thing was missing is that we wanted to know what the spin contributions were at small x. And our error bars were big, and they also straddled 0, depending on the paper that you're reading at the time. But this seems to be an issue. We want to have small x predictive power, and yet we have a large uncertainty in our small x spin contributions. This is the integral from 0.1, which is our upper limit of the small x region, down to 10 to the negative 7. So we're only integrating over small x partons. And this is the sum of quarks and gluons. And we get something that's predominantly negative, but the error bar is too large. The error bar is large because we're getting some positive solutions and negative solutions. And if you were to solve the KPS-CTT evolution equations, those small x dipole evolution equations, you actually find that they grow with this power law in the limit that x goes to 0. So this growing to infinity is expected. It could still be integrable as long as alpha h is less than 1, which it should be already even without saturation of x. But if other corrections come through, we can use saturation of x to bring down this intercept, so that way it's integrable. But the fact of the matter is, it's still a power law. This is going to be plus or minus infinity. But that's the issue. It's plus or minus. The data that we were fitting to, the DIS and CITIS data, is not sensitive specifically to the sign. And even further, it's not actually any specific sign that it's not sensitive to. Some of our dipole amplitudes are just insensitive to the data, specifically our gluon type dipole amplitudes. And that means DIS and CITIS data, no matter, I wouldn't go so far as to say, but we have a lot of data points, but it doesn't seem like it's enough to constrain all of our dipoles. We know this because if I just force, in our phenomenology, I force some of these dipoles to be positive or negative, we do get predominantly positive or predominantly negative results. So really what we need is an observable that is sensitive to those gluon-dominated polarized dipole amplitudes. And we know what that should be. Well, we had a few different options, but we went ahead and took a look at proton-proton collisions. Because just as we saw before, you've seen the picture a few times with deep inelastic scattering, electron or lepton versus a proton, that photon will split into a quark-antiquark pair, but only ever a quark and an antiquark. You can get gluons from the proton or whatever nucleon or nucleus that you're scattering off of, but only ever the one gluon. But if you have a proton-proton collision, you can get a gluon from both sides. And thus you have something that should be more sensitive to gluons and these gluon-dominated dipole amplitudes. Now there's an actual gluon production cross-section or jet production cross-section. That's the data we have access to at the JAM framework where we do the phenomenology. And that's proton-proton to jet. Now there's a typical collinear factorization form, but we're not using only collinear factorization. We're using a small x formalism. Luckily enough, Yuri and Ming, which I believe Bjorn showed in his presentation earlier, Yuri and Ming actually wrote a small x proton-proton parton production cross-section. They did it in the pure gluon limit, so I had to make a little bit of compromises there. But we do see that this cross-section is indeed sensitive to these gluon-dominated dipole amplitudes, G tilde and G2. And while this isn't a jet production cross-section per se, in the double logarithmic approximation, the jet function is just a delta function. So we can treat them at the same, at least at this order. And when we include this new data, we see massive improvements in our uncertainty. 73% for the G1 structure function, and a similar 73% for delta sigma, the quark HPDFs, and the gluon HPDFs. So that is a success. The PP data has successfully constrained the parameters that were less constrained before. And we saw that this actually resulted in a very big reduction in our small x uncertainty for the total helicity contribution, helicity contribution. As Bjorn pointed out, it is closer to 0, and that may imply that there's not much spin hiding at small x. But of course, this is a large NC compromise that we've made so far. Yuri and Ming and other theorists have only gone so far in making a small x proton-proton cross-section. So eventually, when other quark channels are introduced in theory, which we expect to be equally important, maybe this might shift. But the systematic effect that we see is that proton-proton data will constrain our parameters. Whether this will be constrained more positive, more negative, or still closer to 0 remains to be seen, but our uncertainties are much smaller. The only thing that's left is that there is still this asymptotic bimodality. We've constrained the overall uncertainty, but we still get solutions growing positive and negative. And that's where something like the EIC comes in. We're able to construct EIC pseudodata, where we essentially just take our theoretical results and take a look at the EIC yellow report, and we know approximately what kind of uncertainties and smearing and kinematics the EIC will provide. So we essentially take our theory and apply that kind of smearing and treat that as new data and try fitting that again. So we get an approximation of what the EIC's data will help us for our phenomenology. And we see that that bimodality will be broken. Whether the EIC predicts slightly positive G1 in this case, or slightly negative G1, or even something very close to 0, it will still be enough for our small x evolution equations to fit that larger x limit for the initial condition and evolve to small x in a sign definite way. And there we go. That was my final thoughts from the GHP conference. You got to worry about it.
Yeah, thank you. Yeah, nice details of what we saw earlier today. Questions for Nick?
Can you go to slide number 2? There you are talking about polarized Wilson lines and then dipole Wilson lines. So are you talking about the dipole type Wilson lines?
Yes. So in this case, this is just a dipole. Drawn here, I didn't show anything about the spin, so this could be polarized or unpolarized. But this dipole is a correlator or an operator made out of a Wilson line and its complex conjugate Wilson line. The same thing occurs for a polarized dipole. That is essentially just a combination of one unpolarized Wilson line and one polarized Wilson line.
My question is, there are other types of Wilson lines as well, like William-Weizsäcker. Why don't you consider that? Why only dipole type?
I don't know. That's a good question. I guess I never considered that. Other types of Wilson lines. I'm sure if we sandwich some polarized subiconal interactions in between them, we could get something similar. I guess I never considered that. I kind of continued on the phenomenology that was going, but that's something I should consider later.
You guys got a project, so. Okay. All right, let's thank Nick again. So our final talk of the afternoon. All right, I'll give you a 3-minute warning. Okay. All right, so Jose.
Thank you. I am Jose Garrido, and today I will show you the solution that we found to the decay equation using this homotopy approach. So I want you to see this picture. the typical process that we are discussing today is electron colliding with a proton. So let's look in more details the kinematics. We can describe this process with some certain variables. We have this excursion, the virtuality of the photon, and the energy of the process, which we say it is P plus Q. So this is how it will look in a collider, for example, the EIC. And now let's put this picture, but in a paper. So the typical, we draw like this. We say we draw in the in light tone coordinates. We say that the electron is split into a virtual photon, and then fluctuates into a pair, a quark and antiquark pair. That we call a dipole, and the proton is moving in the X plus direction. So we see that the protons creates like a interacts with this type, and so usually this process we describe with this kind of red rectangle. The color is not important, but we call this a shockwave. And we also assume that this quark and antiquarks moves very fast. So we represent this as straight lines. Now, for example, what we measure in the experiment is the cross section. We say it is kind of a convolution with the wave function. This is the virtual photon is splitting into a quark and antiquark. And this cross section that it is described by this formula. We also define this n, which is the dipole amplitude. And I don't use d, but I use n for describe this. So this is how it looks like. And now what happens if, because the quarks move very fast, so we can have emission of a gluon. So we can have real emission and virtual emissions. So after doing this one-step evolution, we will find the decay equation. It looks like this. This kind of equation is difficult to solve analytically, so we will take some approximation. We say that the impact parameter is large, so with that we can simplify this dependence as follows. And it is better don't use this x10. It's better use this R for more clear notation. Now, this is the typical kinematic regions that we are dealing in QCD. We say that for dipoles of this size that are less than this size, we are in the perturbative QCD zone. The ones that are similar to 1 over this QS is the saturation scale. We say it is near the vicinity of the saturation region. And for dipoles larger than 1 over QS squared, we are in the saturation region. So first, now that we have our equation, we usually use this decay equation in the saturation region, but in order to solve, we will need to have some initial condition. So I will solve the equation near this line. Because we are near this line, I can neglect that nonlinear term, and it's reduced to the BFKL equations. We can solve using Mellin transformation. And well, we will have some eigenvalues. And the final solution, well, this is approximate solution after making some saddle point approximation, but it will be kind of this, a constant times exponential of gamma bar C. Here we have defined also many variables in
while doing this, we have this psi, psi-s, zeta, which it is psi-s plus psi. We also find the formula for the saturation scale and some constant. And well, with doing all this calculation, we will see that the boundary condition for nonlinear equation, in this case that we're considering, that is electron colliding with a proton, it takes this form. It need to be equal to n0 at psi equal to minus psi-s, and this is condition for the derivative. Okay, and now let's back to now considering the nonlinear term. Because it's still difficult to solve, we will need to make another approximation. This is approximate the eigenvalue as follows. Sorry. And well, the idea behind this is consider only the leading twist contribution to this eigenvalue. And after taking into account this, our equation will simplify to this type. It's still very complicated, but we can solve. We can make some substitutions, 1 minus exponential of minus omega, and find an equation for omega. This is an implicit equation we cannot solve analytically, but for a small omega, we can solve, and it takes this formula, which is very well known in the context of saturation physics. So far I have described how it is found, this famous formula, in the context of the leading twist approximation, but all this was considering a running coupling of, well, a complete constant that it's a constant, but in reality, it is a running coupling constant. So in order to take into account this, we do the following. Now we consider the quark loop contribution. That is, we need to calculate all these diagrams, sum all this in our evolution. Then what we will obtain is some equation that has terms that are proportional to alpha s times nf. But we need to still consider obtain higher order of these corrections. So we will apply this Brodsky-Lepage-Mackenzie prescription. That means we can take into account infinite quark loops contributions in the gluon lines. And this is very simple. I need only to replace NF as follows. This beta 2 is related as has this form, and it is related to the QCD beta function. So doing this substitution in the previous result, we will be able to resum all quark bubbles. And if we also take the leading log approximation in our equations, we will find finally the decay equation, but with running coupling corrections. We have two models for this. One is that was calculated by Balitsky, takes the following form, and the Kopchakov-Weinberg prescription. This is more difficult. Both formulas coincide numerically. The only difference is that they take different subtraction terms. This is in order to make in order to have finite diagrams. So you can choose whatever you want, but we will take in our analysis this Balitsky prescription. Also, we will take some approximation. For example, that in the near the saturation zone, the dipole size are similar, so we can reduce the kernel as follows. So having that in mind, we will have the same formulas that we derived before, but we will have a different definition for the saturation scale. Also, this XIS will also change its definition, so our initial conditions will be more complicated in this case. So our work was trying to solve again the decay equation, but this time considering these running coupling corrections. So again, we take this leading twist approach. And after doing some algebraic, some tricks to solve, we will find this equation for omega. But it is very similar to the case of the when it is a constant, but we have a new variable, this L, which I define as follows. It is related to this psi, but has now this factor that comes from the running coupling prescription. Now, if we want to try to find a solution that depends of zeta, we will have an equation like this for omega, but it's still difficult to solve. We actually cannot solve with the methods of before. So what we propose is search for another type of solution. We say that our scaling variable is y times L, and we can reduce the equation for omegas as to this. And the boundary conditions will be this formula. But again, we have another problem. This is because this condition for the derivative, it is not a constant, depends of the rapidity. So we need to propose something to solve this equation. So what we propose is propose like a sum. We say we have a omega zeta and a omega prime. And for the omega zeta, we have the derivative condition is equal to 0. And then we solve the equation that we can solve with our perturbation method theory. We also define this new variable, zeta times L minus Ls, which is this formula. And this is the result for omega zeta. We see that after many iterations, it will be equal to the exact solution, so it is right. Now for omega prime, also we found that after many iterations, it reproduced the exact solution. So what is interesting is that we found some analytical solution by, but this time using perturbation theory. Now the total omega obviously is the sum of these two omegas. It takes the following form. We see here that for different, these L minus Ls values will not be very, we will not have some scaling in this case. Now I will introduce you to this homotopy approach. Basically, we have a nonlinear differential equation, and we need to define some L and some NL. And then we can find the solution. Like we can expand. This is a series. We expand in some parameter P. And after that, we take P going to 1 to find the total solution of my problem. So we apply this method to the decay equation. We see for formula, when P goes to 1, takes this form. So we say that the solution is this term plus some corrections. These are the formula for the corrections. So the idea, what we want to show is that the correction, these infinite terms that we have, are going to be small and more small as we go. So we apply, we first define this L as follows. This is the equation I solved previously, so I already do this. And now I do the second iteration. Now I consider this the contribution of this nonlinear term. So the equation for my omega 1 took this form. Unfortunately, we solved this numerically in this case. And after computing omega 1, I can use the formula I showed before, and I compute the corrections. we see the correction are very small, 0.02. And again, I apply this method again and compute the third iteration. This formula for omega-2 again is complicated. I solve numerically, and we see now we have it is more small even. So with that, we can show that the corrections are very small. So finally, if we sum, well, I didn't do all the iterations, but we expect that the omega-3 and so on will be small. And finally, I will show you some final result. This is omega as a function of this variable theta. This is omega considering all the corrections. This is the same, but as a function of L minus Ls. This is a function of theta, not the Greek theta, but the other theta that we know. And this is the dipole amplitude as a function of L minus Ls for different rapidities. This is as a function of the dipole size times lambda QCD at fixed y. And for fixed R lambda QCD, but as a function of y. So we see, for example, in all these plots, we see that the dotted line, which is the zero correction, is in the continuous line, that is with the sum of the first with the second correction, they both are very similar. So the correction doesn't apport too much. So that is what I wanted to show you. And what is the next problem? Well, this is consider a collision of an electron with a heavy nuclei. For example, this lead, gold, or uranium, in which we have many protons in the nucleus. So what is different in this case is that we will use a different initial condition. This is the McLaren-Bennu covalent initial condition. In this case, so we need to again do all this analysis, but not using this BFKL initial condition, but this one. And this is our next task. And well, that is my talk. Thank you.
Hey, thank you. Yeah, thank you. Interesting, very appropriate with the topics both today, this week, and we'll see some more next week. So thank you. But yeah, I want to take a chance. Let's thank Jose and all the speakers of the session. Thank you. So we've survived the first week. It's been a busy schedule, but we hope you have a refreshing weekend. The barbecue officially starts at 5, but they could probably use some help carrying things, setting up. So I encourage you to do that, and it'll be right downstairs. Just smell, follow the smoke, the fire. There'll be burgers. For those of you going into New York, I hope you have a good time. Use the WhatsApp, keep in touch, let people know where you are, go in groups, especially after dark. I mean, it's a big city. It's pretty safe overall, but just be careful. Don't do anything silly. My phone number is there. Alexi's phone number there if you have any trouble. The tourist tips are on the web. I recommend the Brooklyn Bridge. That's free instead of going up the Rock or the Empire State Building for 50. But have a good time, and we'll see you down at the barbecue. So have a good weekend. Thank you.